You are already excited about this object called obfuscation, as well as to outline to you some of the important milestones in the conceptual and technical development of I/O over the years. And I will particularly focus on this JLS construction, which is building I/O from well-founded assumptions, but also touch a little bit towards the end about recent development of lattice-based candidates. This is a talk that I gave already at Eurocrypt, so apology to those of you who have heard it once, but I saw many new faces here, so hopefully it's fine. Okay. All right, so already back in 1976, starting from the first public proposal of public key cryptography, that Diffie and Hellman were, together with other cryptographers, were wondering about whether we can efficiently transform a program, pi, that may have lots of secret inside, into another program that is functional equivalent and hides secrets. And this transformation is what Diffie and Hellman back in the days called one-way compilers, and what we now call obfuscators. So they're efficient randomized algorithms that can take as input a program description, typically it's a circuit, and produce another circuit we call the obfuscated program, with the guarantee that the obfuscated program really computes the same function as the original program, that on every input they produce the same outputs. And now the new program becomes unintelligible. So back in the days, 1976, that cryptography was really pondering about whether public key cryptography exists. And what Diffie and Hellman thought is that if we had program obfuscation, then we can obtain public key cryptography by simply obfuscate the encryption algorithm of any secret key encryption scheme. For example, AES with a random key K. Because the obfuscated program is meant to hide the secrets inside the original program, therefore, this obfuscated program can simply serve as the public key. And in fact, this approach would give us the shortest ciphertext public key encryption known. Okay, so this is fantastic. And what else can we do if we have such an ideal obfuscation of general programs? And here by ideal obfuscation, what we mean is that white box access to this obfuscated program give you no more information than black box access to the original program pi. Well, if that's the case, then it's really powerful because it should really help us to hide any secrets that are not efficiently learnable from the input-output behavior of the program pi. And such secrets are plenty. And in fact, with such an ideal obfuscation that we will be able to help hide sensitive information from the user, such as their DNA, while keeping them still useful. For example, if the user would like to obfuscate, would like to delegate the ability to a doctor to be able to answer certain limited queries on their DNA in order for precision medicine, they can do so by a obfuscated program that has their DNA hard-coded inside, and on input a credential together with the query. What the obfuscated program does is first check if the credential satisfies user's policy, and only so answer the query. And this allows us to enforce really, really fine-grained access control over sensitive data. And we can call this usable secrets. And we can imagine there are many different forms of such usable secrets. For example, we can have an obfuscated cryptographic key that allows the key to perform the same function but protects it from malware. We can have obfuscated authentication token for digital wallets or for digital rights management. Or we can have obfuscated medical records that help us in creating digital health cards. And when obfuscation is combined with other cryptographic tools, such as encryption, we can achieve loads of cryptographic goals, such as for the homomorphic encryption, all what we need to do is to obfuscate a program that has the right secret key hard-coded inside, that on input encrypted input is going to decrypt internally, do the right computation on the decrypted plain text, and then re-encrypt the output. As such, we can implement FHE simple. We can now also change it by allowing the FAST program to output part of the processed output in the clear without re-encryption. And this effectively allows us to implement a different powerful primitive called functional encryption. So these examples illustrate to us that how simple and flexible it is if we have obfuscation in implementing different cryptographic goals. So perhaps it comes with a lot of disappointment, but also not too much surprise that ideal obfuscation turns out to be impossible in general. And the reason is that the left and the right-hand side simply cannot be equal, right? This is what we hope for, but in the left-hand side, with access to the FAST program, no matter how unintelligible it is, after all, the attacker has a program that computes the function pi. However, on the left-hand side, with only black box access, for many programs that are hard to learn from the black box access alone, that the attacker does not have such a program that computes pi. Therefore, these two words are fundamentally not the same. Nevertheless, perhaps ideal obfuscation is simply too strong, and we can still hope that the FAST program can act like a virtual black box as we would like for hiding very specific properties of the program. For example, I can consider the property that for AES with a key K, the property is recovering the key. And then being a virtual black box for property P simply means that one can only learn the property P of pi if one can learn it from the white box access. That must mean that you can already learn it from the black box access. So then the question is that for what kind of properties that the VBB obfuscation is possible? And what was shown in Brack et al.'s work is that even for general predicate properties, property that outputs only a single bit, it turns out the VBB is impossible by showing some contrived counterexamples. However, the good news is that unlike the impossibility of ideal obfuscation, which is really rampant, a counterexample for virtual black box obfuscation is actually rare. And in fact, so far we have no counterexample for VBB obfuscation when it comes to natural properties and natural programs. Nevertheless, we would like to have a general notion of obfuscation that does not suffer from any counterexample. And that is indistinguishability obfuscation. And it gives a really much weaker security guarantee. What it says is that if we started with two programs that have the same size and literally implement the same function, but in different ways, then the obfuscation guarantees that the produced obfuscated program become hard to distinguish. In other words, IO only hides the difference between two implementations of the same program. This is indeed much weaker than VBB obfuscation. So therefore, two immediate questions that arise is this notion still useful, first of all? And second, if so, can we actually construct it? It turns out that those two questions took us decades to answer, and we're still on the way. So let's first look at the useful question. Given that IO obfuscation hides only implementation difference and is much weaker than VBB obfuscation, it's natural for us to ask if I use it to obfuscate a program, what does it actually hide, right? For example, if I use it to obfuscate AES with key K, is the IO obfuscated program still acts as a secure public key? Or weaker, given it, can I actually recover the key out of it? And after we stare at this a little bit, it becomes clear that it seems hard to apply IO security to begin with. Why? Because to apply IO security, I need to find another implementation of AES with key K before I can claim anything. But what would that implementation be? Quite interestingly, in a work by Goldwasser and Rothbaum, they show this strange power of IO, that IO is best possible, through the following mental experiments. In this mental experiment, let us imagine that there is some arbitrary obfuscation of a program pi, let's call it lambda. And because lambda is an obfuscation of pi, it might be significantly larger than pi. And we can think about lambda as the best possible obfuscation of AES with random key k. Now, we can pad the program pi with a bunch of no-op operations to become the same size as lambda. Now, those two really implement the same function. And therefore, we can apply the IO security to declare that the IO obfuscated padded version of pi should be as secure as the program lambda to start with. And what this is telling us is IO is in some sense universal. That if I use IO to obfuscate a program pi, it achieves security that matches the security of the best possible obfuscation of pi, without us even knowing what that best possible obfuscation is and what it is achieving. It just magically achieves the same. And this also gives rise a very, very powerful heuristic that we refer to as the best possible heuristic, that IO without even padding the program pi or with a fixed amount of padding already hides the best possible to be hidden. Okay. But still, we're curious. We would like to know, what does the best possible obfuscation of pi really hide, right? And on this front, that the most possible optimistic view that we could have is that VBB obfuscation is really possible for natural program and the natural property, such as the key recovery of AES key. And in a very recent work, we actually draw a connection between this VBB heuristic together with the random oracle heuristic that we all love. Let's think about what the random oracle heuristic says. It says that given white box access to a real-world hash function, say SHA-3, this amounts to having black box access to the random oracle. So effectively, we can view the code of SHA-3 with a random prefix k in some sense as a virtual black box obfuscation of a PRF with key k. Yeah.
Do you care here about the distinction between VBB and ideal, or you say VBB becomes shorter?
We don't really care, yeah, at this point, yeah. This random oracle heuristic effectively says that SHA-3 with prefix k is an ideal obfuscation of a PRF, yeah. And further, the recent work showed that given virtual black box obfuscation of PRF, we can actually get virtual black box obfuscation of any program. And this is proven in a new ideal model called the pseudo-random oracle. And hence, it gives partial justification for this VBB heuristic. In other words, now, if we believe in the heuristic, then we can use IO to create all these usable secrets that we mentioned before. What about the without heuristics? It turns out that the cryptography has developed.
Sorry, can you go back? So
yeah.
De facto, this is a method, yes? This outlines a method that you are claiming some security for.
Yeah, yeah.
So what is the method?
The method is that give me a natural program,
yeah,
and I use IO to obfuscate it. And I claim that a property P of this program is hidden given this IO obfuscated program pi as much as VBB would have hidden.
No, I mean the one below. What is the procedure of using the random oracle heuristic?
Ah, I see. So we can view that the SHA-3 of key as a VBB obfuscation of a PRF. Yeah. So the random oracle seems to give us an ideal obfuscation of PRF, and that is simply the SHA-3 code. And use it, I can actually build a VBB obfuscation for a general program, if you believe in this random oracle heuristic, in this ideal model. And now the heuristic is to say that any natural property you want to hide from the program is already hidden.
So I'm
Yeah, and this construction is basically the IO construction.
Great.
Yeah.
Do we know of any known schemes which only achieve VBB security but not ideal obfuscation security?
Yeah, you, in generic model, yes, of course. In generic models, I think you can.
I think there is, right? Yes, in the generic model. I mean, usually the ideal obfuscation is easily proven insecure because there is so much counterexamples. Yeah.
That we have, right?
But we don't have really any VBB obfuscation, so we have the negative for ideal obfuscation, but we don't have positive for VBB. Yeah.
Sorry. This is my takeaway. Just tell me if it's correct.
Yeah.
That you can take a general program, okay? You do an IO to it, plus the assumption that you have a pseudo-random oracle, and you can claim that this thing, somehow baked in together, is VBB. Yes?
Yeah. Yeah. All right. So without any heuristic, what Shahan and Water proposed a new technique called the punctured program techniques, and showed that we can use it to circumvent heuristic in most cryptography settings. For example, they showed that if we obfuscate a PRF that is special, that is puncturable, then the IO obfuscated PRF is already a public key encryption. And because that we can actually implement a puncturable PRF using AES, this would already give us the shortest ciphertext public key encryption. We can also use this technique to implement a fully homomorphic encryption, interestingly without relying on any circular security, and the functional encryption primitive, which is currently only known under IO. And the community has developed even more applications. Yeah, please.
Can you slide so wouldn't this require AES to be puncturable, which is not?
You can use the GGM paradigm on top of AES
so
to make it puncturable.
Okay.
Yeah. And the cryptography has built up an entire arsenal of using IO, showing that it acts as kind of a master tool that IO with minimal hardness conjecture such as NP not equals to BPP already implements most cryptographic goals. This includes classical goals such as having one-way function with a polynomial number of hardcode bits, to new applications such as witness encryption and deniable encryption, as well as to futuristic applications like publicly verifiable quantum money, and having connection to complexity theory, such as implying the hardness of Nash and implication connection with bounded arithmetics. So, and with all this, we see that IO enables us to build a Obfustopia in a relatively simple and flexible way. So now the question turns to, can we have it, given that it is so useful? And as a first thought, the task of building IO is that, what about I just simply output the truth table? Give me the program, I give you the entire truth table that contains the outputs for every possible input. And this would really achieve perfect security because for any two programs that implement the same function, the truth table would be identical. And this also tells us that another view on IO security is that it should permit revealing the entire truth table, and that is the only information that is revealed. Obviously, the problem is that this approach is inefficient. The truth table is exponential in size. We cannot produce it. Therefore, the task of IO is to come up with some kind of special encoding of this program that I will represent graphically as a box with the program written inside, and the box is opaque. Opaque means that you can't really see this program encoded inside. Given this special encoding, we can evaluate the arbitrary input x to obtain the output pi of x in the clear. And this can be viewed as evaluating the universal computation U with the input x hard-coded inside on the secret program as the actual input. And security is that this special encoding should reveal the truth table and nothing else. And hence, it's kind of like an exponential compression of the truth table itself without revealing anything more. So it would be helpful for us to kind of get a grasp of what it is asking by comparing it with fully homomorphic encryption. If we use fully homomorphic encryption to encode the program pi, then by homomorphic evaluation, we know how to obtain an encoding of the output pi of x. The problem is obvious, is that I don't want pi of x encrypted, I want pi of x in the clear. And what is the way that will allow us to extract the output in the clear safely is unknown. It will also be helpful to compare with another useful primitive that's pairing groups. Suppose that we can magically obtain the output encoded in the format that the output is in the exponent of the pairing group. Then we can use the zero testing capability given by bilinear map and pairing groups to extract this output in the clear. So now I can extract. The problem is that then it only supports degree 2 homomorphic evaluation because of pairing, and cannot support arbitrary function evaluation. Therefore, a natural approach towards I/O, which was taken in the breakthrough work by Garg, Gentry, Halavi, Rakova, Shahai, and Waters in 2013, is that they give the first I/O candidate by using the first lattice-based candidate multilinear maps. And the multilinear map is a really powerful generalization of the bilinear map that we have just saw. Like bilinear map, it also supports zero testing to allow us to extract the output into the clear. But now it can actually support higher polynomial degree homomorphic evaluation on the encoded values and hence support evaluation of arbitrary program. And soon after this first candidate construction, there came an explosion of I/O constructions based on many different proposed candidate multilinear maps. And it seemed back then that the long-awaited spring of Obfustopia has finally arrived. Unfortunately, this spring was quickly turned into winter through a class of very powerful zeroizing attacks. And the community, of course, didn't just wait and quickly built up lots of defenses, including proposals of repairs to try to immunize these prior I/O constructions against these attacks. Today, we also have many other approaches towards I/O using different kinds of math, such as affine determinant program or local mixing. But nevertheless, that overall, that it seems like I/O was not yet on stable ground at that point. And in fact, this all happened during the 2015 Simon's cryptography program. And I remember that amid this entire confusion with the attacks and the repairs, it just seemed that we were watching a perfect scientific thriller unfolding in front of us, that there's a protagonist, I/O, is super fascinating, and then she is like mysterious and challenging, right? And what I thought at that program was that, well, given that we have tried lots of different direct heuristic constructions of I/O, perhaps we should also invest in different approaches. And since then, a different line of research has started surrounding this question of what is the minimal object that actually imply I/O. And the rationale is that perhaps by beefing up security reductions, we can build I/O from smaller and smaller primitive until we isolate that hardcore. And then we can perhaps either instantiate heuristically or provably. And the two powerful reductions that has arisen. One reduction tells us that to build I/O this powerful primitive, it suffices to build simpler tools, such as functional encryption and exponential efficiency I/O. Another class of reduction tells us to support arbitrary complex program, it suffices to support much weaker programs, such as NC0 functions, if we're willing to assume certain simple PRG exist, or LWE samplers, etc. And all these reductions really fueled kind of a race down to the bottom of the well, which was trying to build I/O based on simpler and simpler, weaker and weaker multilinear maps, all the way down to using just two linear maps that we already have, except that they all still rely on some new type of assumptions. So despite of this continuous progress, back then it still seemed unclear whether we can reach I/O without assuming any new assumption tailored for specific constructions. And this changed in 2021 and 2022 that into joint work with Ayush Jain and Amit Shahai, we built IO from 3 well-founded assumptions. This includes learning parity with noise, however, over larger fields, the existence of simple PRG local ones that are computable by NC0 circuits, and decision linear over symmetric bilinear maps. And all these assumptions need to have sub-exponential security level. And in a more recent work by Vinod and Nikon and friends, they show that this local PRG assumption can be replaced with a local-ish assumption that is sparse LPN. And the good news is that all these assumptions we are familiar with, it has been used in cryptography before us using it to implement IO, and they also have connection with other fields that builds up a rich literature for studying their hardness. All right, so next what I will try to do is to convey to you some high level, I have half an hour, okay, good. To convey to you high-level ideas about the JLS construction, and you're gonna hear more details right after the break in Nikon's talk. Recall that the goal of IO is really to give us an exponential compression of the truth table without revealing more information. And we're gonna rely on this first type of reduction, which is that this task reduced to a much simpler task, called the exponential efficiency IO, or XIO for short. What XIO asks is much weaker. It says that I just want polynomial compression instead of exponential compression, meaning that we allow the obfuscated program to have size that is sublinear in the size of the truth table instead of being logarithmic. And furthermore, we're gonna only handle those special functions where the truth table, the entire truth table size is polynomial, and meaning that the input length is logarithmic, as opposed to handling normal program where the input size is polynomial and the truth table size is exponential. The reduction shows us that as long as we can implement this kind of XIO, we can already have IO. And this may seem very, very powerful, but it turns out the idea is simple and what we are familiar with. The high-level idea behind the transformation, which is the idea behind functional encryption to IO transformation, is that I can view this gigantic exponential-sized truth table as a collection of tiny, tiny polynomial-sized truth tables. And by applying XIO, we can compress these tiny truth tables into slightly smaller ones, say m to the 1 minus epsilon. Of course, this is just very little compression, but the good news is that I don't have to stop there. By just keep applying this compression recursively, we will be able to eventually reach a polynomial-sized encoding, and that is the true IO obfuscation. And this picture should look familiar to you, and indeed, we can view this as the functional version of the classical Goldrake-Gowas or Macaulay transformation for pseudo-random generation to pseudo-random function. Okay, so now that we only need to manage to compress a polynomial-sized truth table slightly to sublinear size, this task turns out to be still challenging. And the difficulty now comes from the fact that the computation itself is very complex and high degree. And in fact, to hide the original program pi, I need to be able to evaluate it in a way that all the intermediate evaluation values remain hidden. Because suppose any intermediate value were revealed, then it would help me to reverse engineer the original program pi. And we're called this kind of computation a sacred computation. And the difficulty is that we need to carry out very high degree and arbitrarily complex sacred computation. In order to address this difficulty, the key idea is that we're going to transform the computation into a different format such that only a very, very simple degree 2 step in the middle needs to be hidden. And of course, we're not magically letting go the rest of the complexity of the computation, just that the rest of the computation can be performed now publicly without hurting security. And if that can be done, then we can hope to use bilinear maps to handle the tough degree 2 secret computation in the middle. And the challenge of doing this is as we are transforming the computation from one form to another, the size of things tends to blow up. And we really need to make sure that the program encoding remains always sublinear in size comparing to the truth table. And next, let's see how to do this. We're going to do this in 2 steps. In the first step, we reduce the secret computation to NC0. And in the second step, we reduce it to degree 2. Well, to compress a computation into NC0, this naturally brings up the notion of randomized encoding proposed by Ishai and Kushelevitz based on Yale's-Gabel circuits. What it allows us to do is to take a very complex computation. The one being done here is evaluate the universal circuit on the secret program pi to reveal the polynomial size truth table. And it will transform it into a randomized computation, which produces what we call a randomized encoding of the computation u of pi, and we denote it as pi hat. And the feature is that the encoding can be evaluated, decoded in the public to reveal the truth table with the guarantee that it reveals no other information about the program pi. And furthermore, the randomized encoding can be done just in NC0 circuits. So this would fit perfectly our purpose that we now only need to compute the encoding itself secretly while leaving the decoding in the public. There's only one issue here, which is that the encoding requires randomness. And where does this randomness come from? Well, this randomness, unfortunately, I cannot hide it by encoding it together with the program pi together because the length of the randomness scales with the length of the output, the truth table, and that is too long. Well, here we can just rely on the classical idea that we can always expand out pseudo-random coins from a much shorter PRG seed. And this will make the input of the encoding to be the sublinear size seed, and hence I can afford to encode it together with the program pi while maintaining the sublinear size constraint. And everything is still in NC0 as long as my PRG is simple to compute, computable in NC0. Therefore, now we have reduced the task of building XIO to the task of building XIO for just NC0 circuits. This is fantastic. Unfortunately, this task is still difficult. Well, NC0 functions, let's remind us how they look like. Each of the output depends only just a few input elements. That is called the locality, then it is a constant. And such Boolean function can be rewritten as a multilinear degree D polynomial. The issue is that how can I perform a secret computation of arbitrary constant degree? Well, the only thing that we know how to do is to evaluate the degree 2 secret computation. And this is using the classical tool of pairing. And in fact, that trying to get out of this confine of the degree 2 secret computation imposed on us by pairing has been a long-standing goal that cryptography has been working towards. What we could do is that we can indeed extend the computation slightly by adding a public component to it. And what I mean is that we can handle this kind of computation where it contains 2 part input, a public part P, and together with a secret part X. And we can afford to evaluate a complex NC1 function on the public part, and its output, together with the secret input, is fed into a degree 2 secret computation to produce the final output. And using pairing, that we can show that we can have XIO for this type of special computation. More specifically, every output element can be written as the inner product between the degree 2 monomial of the secret input X together with a vector computed from the public input through some complex NC1 computation. Okay, Nevertheless, this indeed extends the computation quite a bit, but nevertheless, it doesn't address the fundamental gap that the secret computation I want to perform has constant degree, but here we can only afford degree 2. So once again, that we're gonna rely on transforming the computation itself. We would like to transform the computation from this format to this format. And to do so, it means that I need 2 transformations. One for input preprocessing to convert the original secret input into 2 parts, one part public, one part secret. And the second, the function transformation to turn the NC0 function into this kind of NC1 public computation plus a degree 2 secret computation. And the secret source to do this transformation turns out to be LPN over larger fields. What really gives us is a very simple homomorphic encryption scheme for just NC0 functions. But it has the unique feature that we can have degree 2 decoding. Okay, so let's see how it works. So recall the LPN problem. Here we extended from Z2, the classical Z2 setting, to the ZP setting, where P is a prime, where we all know that given a linear system of equations where A is the public random coefficient matrix, and C is A times S prime, where S prime is a secret random vector, we can solve this system efficiently to learn what is S prime, given A comma C. What LPN says that it's hard to decode how to solve as soon as we add a little bit of noise, and it's related to the hardness of decoding random linear codes. So here the noise are sparse noise, where the noise vector, each of the entry EI in it is kind of a Bernoulli noise, where with inverse polynomial probability, 1 over k to the delta, this entry is non-zero, and with most of the probability, it is 0. When it is non-zero, it is simply going to be uniformly random over this large field Fp. And here we allow a fairly small error rate, or fairly large error rate, which is 1 over k to the delta for any delta between 0 and 1. And furthermore, once we have the hardness of recovering the secret S prime, we can also show that it's hard to distinguish the C component away from a random vector from the field. And this question has had a long history of studying encoding theory, and the best known attack so far runs in sub-exponential time. And I want to point out that when delta is smaller than 0.5, meaning that the noise rate is high enough, that it is actually unknown whether this assumption implies public key encryption. Hence, this is, in some sense, a symmetric key crypto assumption. Okay, but with this, it's very easy to implement a secret key encryption scheme. If I want to hide a vector x, I just added to the C component, which is pseudo-random, acts as a one-time pad to hide the secret x. The S prime is going to be the secret key of the secret key encryption scheme. And each of the row can be viewed as a ciphertext CTI containing the coefficient vector AI and the scalar CI that is an encryption of the element XI perturbed by some noise. And the feature of this encryption, similar to LWE-based encryption schemes, is that they have approximate linear decryption. That the inner product between this ciphertext I with this vector S, which is minus S prime concatenated with 1, will give me the right encoded element Xi perturbed with some noise, which is only non-zero with a very tiny probability. So most of the time, it actually just returns the right output Xi. The nice part of approximate linear decryption is that it immediately affords limited homomorphic evaluation. Why? Because if I simply multiply the decryption equation of 2 decryption and rewrite the decryption equation as the inner product of the tensoring of the ciphertext vector with the or degree 2 monomial over the secret vector S, this will give me Xi Xj, the product, plus some noise. And still, the noise is with high probability 0. And we can extend this tensor ring to handle any constant degree polynomial evaluation. And this will give me a ciphertext now written in the matrix format. It can be decrypted by multiplying with all degree D monomial of the sacred vector S to produce F, the constant degree polynomial evaluated on corrupted input. And this can be rewritten as the right output corrupted by some error vector err. What's nice is that if the original function we're evaluating is not only constant degree but also local, NC0, then the error vector is actually sparse. And this can be seen because an NC0 function, every output element depends only a few input elements. So because the input element is only sparsely corrupted, that each element is wrong with a tiny inverse polynomial probability, an output element is only wrong if one of its neighbor is wrong, and hence by a union bound that each output element is only wrong with slightly increased probability. Right? And therefore, we get that LPN-based encryption give me homomorphic evaluation of NC0 function with approximate linear decryption still, where the output is corrupted still with sparse noise. Okay.
So Rachel,
Yeah.
this is not like interesting as a homomorphic encryption in the standard sense because the ciphertext is bigger than just writing the output, right?
Yeah.
The concatenation of
Yeah.
it. But I guess the point is that the decryption is very efficient, like more efficient than computing the function, right?
Yes, the decryption. The magic is in the decoding. Yeah, so far nothing particularly interesting has happened. And the interesting thing is how complex the decoding is. Well, we've already said that the decryption is approximately linear, but if you think about it from the perspective of correct decryption, that it's actually insecure to reveal the noise vector in the output. Why? Because as soon as I evaluate the noise vector in the clear, we actually turn everything into a linear system, and you can always just solve it to learn what's the secret key is. So a proper decryption is supposed to do error correcting, right? Given that the noise is sparse, it's supposed to do error correcting to recover only the actual output f of x. But once we throw error correcting in, the decryption is actually very complex, right? But this is not strange at all because we know decryption cannot be too simple. There are simple impossibility results that decryption cannot be constant degree, in fact. Then I want to say what we are aiming for, which is degree 2. So some relaxation is necessary. What it turns out that we're not asking for a proper degree 2 decryption, but rather we can relax it to allow the decoding secret to depend on all the secrets. It can depend on the secret key S, it can depend on the function evaluated, it can depend on the original input, it depend on the original noise. In other words, that we just need to create a decoding secret that is tailor-made for opening just one output ciphertext C of F, and it is not for general purpose. With this relaxation, we hope for very simple degree 2 decoding.
Sorry.
Yeah.
That you do depend on every one of these components, but the interaction is NC0? Or,
So x could be some arbitrary function of these things. How it depends on it, how complex that dependency is, I don't care. I just care about given x, this particular cipher, output ciphertext can be opened using just degree 2 computation. Yeah.
That's a capital X to be f of little x?
Exactly, yeah. The additional constraint is, remember, we always need to make sure that everything is succinct, right? So hence they rule out the trivial way, which is set x to be f of x, then decoding does nothing. Instead, we want this decoding secret to be short. Its length is smaller than the length of the output. Now it's non-trivial. So now we see that what if that I just included this error vector which can be computed knowing all the secrets, in my decoding secret, and then using the approximate linear decryption and remove this noise vector, I obtain the output exactly. And the problem is the error vector is actually pretty long. Its dimension is as long as the output itself, and I cannot include it directly in the decoding secret. But the good news is that the error vector is sparse. That is the feature that we have not used. The hope is that we can compress this sparse vector into a smaller version that is much shorter, sublinear in length, and using just degree 2 computation, we will be able to expand it back to the original sparse error vector. If we have such a compression and expansion algorithm, then we will be able to have a short decoding secret where decoding performs the expansion, and then everything will be in degree 2. Okay, to just give you a very tiny taste that why sparse vectors are amiable for compression should not come as a surprise. And here let's consider the toy example where my error vector is so sparse that it contains only a single element that is non-zero. But the tricky part is that you don't really know where that non-zero element is, and you cannot afford to give out where it is. And the trick is that we can always arrange this vector as a matrix of square root of m by square root of m size. And this error vector is going to, this error element is going to land in some row and some column. And everywhere else in this matrix, it is 0. How do we compress such a matrix? Well, very simple. That we can write it, it actually equals to the product of the column vector with W in row L1 and a row vector with 1 in column L2. Okay, so this is kind of a low-rank decomposition. You can see that this method is also going to generalize for a few more noises. And the compressed version will indeed have sublinear in size. In this simple case, it's just square root of m size, and expansion is degree 2. In order to handle arbitrary inverse polynomial noise, we will need some more ideas, but this could be done. Okay, so in summary, that the LPN homomorphism allows us to evaluate the NC0 function homomorphically on LPN encrypted ciphertext to produce an output ciphertext for which there exists a very short decoding secret which contains all the degree D monomials in the secret vector S, as well as the compressed version of the output error vector. And everything is sublinear so far, and the final decoding step is just degree 2. And this more or less gives us XIO from this type of computation, as we mentioned, can be protected. We have XIO for using pairing. And now we can go to XIO for NC0 by transforming an input X. How do we transform it? We encrypt it using LPN and produce the corresponding decoding secret. And the computation F turns into homomorphic evaluation of F in the public and the decoding, secret decoding in the secret. All right, so this concludes the JOS construction. Okay, all right, so now that we have I/O, we kind of build the entire Obfustopia on top of it. And they are now sitting on these 3 assumptions. An interesting observation is that there's actually no lattices involved. This means that it creates an alternative pathway to some of our favorite primitives, such as fully homomorphic encryption, without relying on lattices at all. Of course, we're just barely scratching the surface, right? There are so many wide open questions, such as what are the minimal assumptions that could imply I/O? It's rare in cryptography that we rely on putting together so many different sources of hardness. Usually 1 source is enough. But here we need 3. And can we rely on less number of assumptions? Can we remove this local assumption? Can we show that the polynomial hardness actually suffices instead of relying on sub-exponential hardness? Can we have more efficient constructions? The current construction is, don't even think about to implement it. Can we have post-quantum security? Currently, the pairing primitive that we use is broken by quantum computers. And in fact, can we just have I/O from the powerful paradigm of lattices alone, which would be a dream result for everyone? All of these questions are really related with this challenge of building lattice-based I/O. And the grand goal, of course, is I want to have I/O from just standard lattice assumptions, whatever standard mean to you. And what we're going to do is that so far, we don't have it. We're very far, right? If we restrict to only lattice-based candidates, we have what? Multilinear map. And we have a very recent, interesting line of work, which are candidates inspired by FHE. That's all what we have. Now, I've done this a couple times, but it's always fun for everybody to see this. Let's do a poll where I want to see where the community stands. Where please raise your hand if you're very optimistic that we can have I/O from standard lattice-based assumption.
Can we change the standard or something?
Your standard is by your own merit.
Wait a few
Judge,
years, you can just call current assumption standard.
judge your standard by your own merit. Yes, raise your hand if you're optimistic. Interesting. A few hands. Okay, all the ones who have raised the hands are people who are still working with this. And then who are B, half and half? You know, I really don't know where this is gonna go. This is everybody. And then C, a few ones who are brave enough to say, I don't believe in this. Nobody? Nobody is brave enough to say you don't believe in this? Oh, this is true optimism. Okay. Well, hopefully this... Huh? You counted that standard if you believe that standard. I believe in that standard, yeah.
For example, it doesn't, by the way, everything is exponentially hard, right? Those are some choices.
Yes, it's exponentially hard, yeah. But there is some hope, like for example, in the pseudo-random oracle ideal model, we show that I/O can be built from polynomial hardness.
Oh.
Yeah. So heuristically, that we believe that the sub-exponential security is not necessary. Okay, so this shows us that we really need to have the room to play because we're so far from the answer, we have no idea. Our answer is no better than a random guess. So we need to have the room to play so that we can fail and learn from our failures hard, right? And particularly noted that in the more recent line of FHE-inspired candidates, the works have put in effort to formulate new simple-to-state lattice assumptions that can provably imply I/O. And all of these assumptions belong to this class of LWE with hints. Okay, so let's take a very quick look. So we're familiar with the circular LWE assumption where the LWE sample A and SA plus E is used to hide a function of the secret itself. And we still conjecture that this circular sample is pseudo-random. And one of the greatest results in cryptography is that this assumption implies a fully homomorphic encryption. And what about XIO? That seems very close, right? And the natural idea would be that produce a program encoding, which is using circular LWE samples, and then use the homomorphic evaluation capability we already have to produce an encrypted truth table. Now the gap is clear that I need to somehow get the truth table in the clear. And the great idea in the work that is proposed by Braksky, Dr. Lingard, and Malavolta is that what if I can have a very succinct and short opening that allows me to break open the output encoding to reveal the truth table in the clear, but somehow this opening is tailored to the output encoding and does not completely break the original encoding of program pi. Okay, how can we achieve that? And that's why why LW with a hint was born, where the hint essentially are leakage of the original circular LW samples, and as leakage can depend on everything, right? And the leakage is supposed to facilitate building this succinct opening setup, but clearly this is also a very delicate business because we need to get it right so that this leakage allows me to open some encodings, but keeps the rest intact. Okay, so this is the difficulty part. So what kind of leakage can do this, right? I clearly, if I give out the secret S, I can break open everything, but there's no security left. So the leakage needs to be a little bit tamer. And so far we have explored the various different forms of leakage. Candidate number 1 is some weird function of the secret S, right? And candidate number 2 is some kind of inhomogeneous trapdoor that can map one LWE matrix to another one. And finally, that there is another type, which is an opening of a zero ciphertext with respect to a public key that I will talk about later. In some of the scenarios that these hints also naturally gives you noise leakage. It gives you some kind of function of the noise. And it turns out that the Achilles heel of all these assumptions is that so far attacks can break them by looking at the hints and the noise leakage themselves, because they have lots of structure inside, and by looking at them, we can extract information. Okay. So as a very modest, tiny step, we can ask that, can we create LW with hint assumption where the hints are provably secure? And this is the goal that we set out to do in this work, where we proposed the circular security with random opening assumption with Aryush Jain and Yao Qin here. And what we can do is that in this assumption, the hint itself is marginally random. So therefore, by looking at the hints alone, you cannot get any information. And in addition, there's no natural noise leakage. And therefore, no vulnerabilities in hints alone. Okay, so what are those hints? Those are actually openings of Regev's encryption of ciphertext of 0. So let me quickly tell you how these hints look like. Hopefully, we're familiar with Regev encryption, where the public key are LWE samples with respect to a public matrix B. And the encryption randomness is a small norm matrix R. And when we multiply these, it produces a 0 ciphertext. This is a ciphertext that encrypts 0, which is another LWE sample. And an opening to such a ciphertext with respect to a public key means a small normed matrix R that is mapping the public key all the way to the ciphertext. Now, what is a random opening? A random opening simply means sampling this small normed matrix R from the good IID Gaussian, with IID Gaussian entries conditioned on that B bar times R is the ciphertext. So that means a random opening of a ciphertext with respect to the public key. So the Regev encryption has this very nice equivocability property. Well, in the real world, we know that the public key has structure. It is LWE. And the matrix R is typically sampled as Gaussian, and it produces a 0 ciphertext. But we can always typically flip the order of sampling. The first experiment can be rewritten as that I first sample a 0 ciphertext uniformly randomly, and then I figure out what is the randomness R that satisfies the constraint. In the ideal world, the public key B bar becomes truly random. In this case, that no matter what the ciphertext matrix is, there no longer exists the notion that something being a good encryption of 0. But no matter what the ciphertext matrix is, this distribution of a random Gaussian R that satisfies the constraint B bar R equals to the ciphertext is always well defined. And in fact, that this distribution can be efficiently sampled if we sample the public key B bar with a trapdoor. Okay, so now the CRO assumption starts with, as a first step, the circular security assumption, which says that the Regan public key together with some circular LW sample is conjectured to be jointly pseudo-random. So this is the standard circular security assumption. And the new game in town is that we have random opening. Okay? This means that in both the ideal and the real distributions, we're gonna give out additional hints, which are random opening of some zero ciphertext. But random opening to which zero ciphertext? This zero ciphertext naturally has to be correlated with the circular LW samples for it to be useful, and those are computable using a special evaluation procedure, algorithm F, from those circular samples. Okay? And the constraint is that to make sure this hint has no structural vulnerability standalone, we have the constraint that it needs to make sure that the ciphertext is truly statistically a good zero ciphertext in the real world. Then by definition, the random opening R is truly marginally Gaussian. With this constraint, we can imply that the ciphertext produced in the ideal world is pseudo-random, and the random opening is a pseudo-Gaussian. Okay? What we showed in the paper is that for some fully specified distribution of circular LW samples and a fully specified evaluation procedure F, this assumption implies XIO. And what we would like to say is that this basically provides a new cryptographic target. We can do more things to try to attack it.
How does the challenger sample R?
How does a challenger sample R?
The trapdoor in both left and right? I don't
Yeah, I can tell you later, but let's not get into this right now. Let me first finish. Yeah. Okay, so we have a new cryptographic target. Now, it's hard to find an attack on the LW samples alone because of circular security. If you look at the hints alone, it's marginally random, can't do anything. If we look at a trivial combination, which is multiply B bar with R, it will produce this ciphertext, but which you already know from the circular LW samples. So we need very non-trivial ways of combining the LW samples with the opening. Okay, so here's where we are in 2025, that we have made some progress. We have construction based on good assumptions. We are exploring lattice-based assumptions using LW with hints. And we don't know where does the future lie. Of course, what we hope for is in another 10 years, in the cryptography program at Simons in 2035, we're going to have the true Obfustopia where IO is both theoretically sound and practically attainable. And of course, at this moment, IO is at the very, very theoretical corner of cryptography and with loads of good theoretical foundational questions to solve. Should we think about practical IO at all? Is this too ambitious, or this is naive, or this is not interesting? I would like to say that this answer to this question is simply irrelevant because, first of all, it's a worthy subject to study. We pick our battle, we don't pick our outcome. Second, great things always come out when you strive for ambitious pursuits. Even if we don't get there, there will always be side outcomes. Second, lastly, we're familiar with the fact that the efficiency is a work of progress, right? All of the cryptographic tools are on a spectrum, and over time, they're all moving towards practice. And lastly, I would like to say is that the time of today is different from the past. And over the years that with the rise of applied cryptography, the community has really bent the curve that I believe what's theoretical and what's practical has become closer than ever. How close, I don't know, but closer than ever. And in particular, the energy comes from a lot of new algebraic techniques and ways to work with principled new assumptions. And this means that if today I have a direct algebraic construction which avoids such as recursion, reduction over reductions, it's actually much faster and more hopeful to bring it to the practical side. And what is close to direct algebraic, we have candidates on XIO, not yet FE, but potentially in the future, that are close to direct algebraic. We need more things, in particular, big bounty on more efficient ways of transforming XIO and FE to IO. But take the opportunity. Okay, all right. Wait.
Let's take like one or two quick questions. Anyone say?
You mentioned, I forget what the name of the heuristic was, but it's like you can add a fixed amount of padding and that's like as good.
Best possible heuristic, yeah.
Is that justified in that heuristic model? I forget what it's called. Random oracle something.
No, that has nothing to do with the pseudo-random oracle model. Yeah, that one doesn't have any justification. That's why it's a heuristic, yeah. It would be great if we have some reasoning of it.
Can we do a poll on whether this will happen?
Yeah, let's do a poll with this, whether this is going to happen. How many people believe that in 10 years we will have semi-practical I/O? Okay, let's say obfuscation of AES under 1 second.
10 years?
10 years, yeah.
The question is, what's your definition of practical?
Yes, I said obfuscation of AES.
Somebody's going to implement it?
Obfuscation of AES, which runs under 1 second. Is that concrete enough?
Concrete enough to somebody.
I think 1 hour is
Under 1 hour, okay. Amisha says,
No,
under 1 hour.
Under what assumptions?
Any assumption.
Doesn't matter. Assumption that
Unbroken assumptions. Unbroken assumptions. You believe so, Moni? Yeah.
How long does it take now?
How long does it take? Under-specified. Nobody knows.
Under currently unbroken assumption, including.
I think mostly people don't implement, yeah. You can examine them by eye and maybe, I think it's definitely above 1 second. Maybe 1 hour is possible for some constructions, yeah.
For evaluation purposes, what's the current best, say, FAQ evaluation of AES?
That I have to ask the audience. What's the best FHE evaluation of AES?
Millisecond non-amortized or amortized?
I think amortized.
Amortized.
Yeah, okay. Thank you.